All right. We're going to start with, what is a differential equation? What do you remember about differential equations? Notes were on the table coming in. What happened to my toolbar? All right, we'll figure it out. Differential equation involves slopes, right? What is a differential equation? Okay, so tangents are involved, yep. In its most simple sense, it's an equation that involves a derivative. And what's your job if you're given an equation involving a derivative? What's your job? If you get an equation involving a derivative and it's a differential equation, what are they going to ask you to do? The command is solve. Solve a differential equation means what? Find the function. I realize that first question on your notes is a little different than this, but we decided that what is a differential equation is a better question than what was there. Okay? So, yes, it is. All right, so go ahead and write an equation for this one, will you? A function is given such that its slope is always the square of the x-coordinate. What is the function if it goes through 1, 4/3? We did something like this the other day. Take 45 seconds or so and see if you can come up with it. All right, so at this point, slope is always, we're looking for a slope function here. The slope function is the square of the x-coordinate. So dy dx, or y prime, whatever you want to use here, dy dx is x squared. Okay? I want the function. If I have its derivative, how do I get the function? Integrate, or anti-differentiate, however you want to do it. This ends up being y equals x cubed over 3 plus the constant of integration. This is similar to what we did on day 1 of chapter 8, isn't it? At this point, once we've anti-differentiated, we use the initial condition of 1, 4/3, and we get a c value of 1, which means the function y equals x cubed over 3 plus 1 is the particular solution. You could check by doing what to y? We could check our answer, check to make sure it's right by doing what to this? Even better, take its derivative. If I took the derivative of this particular solution, would I get the derivative equation that I started with? Yes, that's what we want to go. So this, just review of vocabulary, this is the general solution, and the particular solution is the one that goes through the given point. Good? Okay, what's nice about that is the derivative only has one variable in it, and we are used to anti-differentiating x's. Polynomial functions are easy to anti-differentiate, and that's something that's nice here. Go on to the next example, turn your page, and these are what are called separable differential equations. A separable differential equation is an equation in which you can algebraically separate the variables. Separate means get them on opposite sides of the equation. Okay? Most times, a lot of these differential equations will have x's and y's on the same side of the equation. There'll be an operation with them. We'll talk throughout the hour here about some of those operations that are typical. But let's start with this one. If this was on an AP exam, an FRQ, You can, well, we will dig into some of the scoring rubrics a little bit later. Probably on Monday would be a better time for that. But if you're asked to find a particular solution for a differential equation, the first step you need to show, and if you don't show it, you'll get 0 out of 5, I guarantee it. Okay, you have to, number one, separate the variables. That's why I've got it here. The first step is to separate the variables. You have to find a way to get everything with an x on one side and everything with a y on the other side. Spatially for us, I feel like it makes a lot more sense to have the y's on the left and the x's on the right. Doesn't really matter, but I have a tendency to move everything that's got a y in it to the left side, everything that's got an x in it to the right side. So do you see an algebraic process that we can use to get all the x's on one side and y's the other side? Some of you are doing this. Cross products, right? We can go y dy equals x dx. That is step one. And if you don't show evidence that you did that, I promise you, you'll get 0 out of 5 on this portion. Okay? You have to separate the variables first. There are other ways to do these, but you have to separate the variables in order to get points on the AP exam May 7th. Okay? Number 2, integrate. Integrate the left side, integrate the right side. What is the integral of y with respect to y? Y to the first. How about y squared over 2 plus c, right? I'm not going to write the plus c on the left. I'm going to go x squared over 2 plus c on the right. You don't need two constants of integration because you could add them together and you just get another constant. It's easier to solve for one constant than it is for two. Okay? And so far? This is where you, if you listen to another calculus teacher, you might end up with a little bit different approach here because there are multiple ways you can go here. I'm going to suggest a method that after you integrate, that you use the initial condition to solve for C. It's not the only way to go here, but I think it helps us organize a little bit if we pause and find the C value now and then find the particular solution in a moment. So the initial condition is 2, 4. So for part 3 here, I will put in 4 for y and 2 for x. C is 6. Okay. Number 4, substitute C back in and solve for y. Okay. Step 4. Y squared over 2 plus x squared over 2 plus, sorry, there's an equals in here. Sorry, guys. Y squared over 2 equals x squared over 2 plus 6. Okay? There's a detail we still need to worry about here. Hold tight. Solving for y, what should we do? Multiply by 2. That gives me y squared equals x squared plus 12. Now what? Square root. And I get y equals what? Technically, it's the absolute value of y. We many times just jump to this. Plus or minus the square root of x squared plus 12. We are looking for a particular solution. Is that a particular solution? No. That is 2 particular solutions. I have to now, number 5, if this is kind of an optional step if the problem calls for it, but step 5 would be to use your initial condition again to check that you got the right particular solution. Okay? So here, since it gives me 2, 4, and you don't need to show all of this, but you need to, at least in your mind, check. It gives me x equals 2, so I'm going to put in x equals 2, and I'm going to find out which one of these operations gives me positive 4. Which one gives me positive 4? The plus in front of the square root. So the particular solution for the first one is y equals the square root of x squared plus 12. Okay? I want you to know that's not the only way to go through that process. You might see other teachers show it a different way. If you're looking for awesome math teachers on YouTube, you might find a teacher that does that a little bit differently. But what's important is that they would get that same final result. And there's a lot of different places you can solve for C. So if we look at that, and this one here is to kind of demonstrate how that initial condition influences your final answer. So if instead of going through 2, 4, it went through 2, negative 4, I'm going to go through this quickly, but hopefully you can bear with me for a moment. If I go back to this, if I use this initial condition in my step 3 here after I integrate, I would get something that looks familiar. 16 halves equals 4 halves plus C, which leads us to the conclusion that C equals 6. You with me? Okay. So then I get back to this again, y equals plus or minus square root of x squared plus 12, right? But since it goes through 2, negative 4, which particular solution do I want? The negative. All right? All right, will you on your notes, will you cross out example 2? Not that it's a terrible example, but when we were going through it, we ran into a little bit of a snag that we don't want to be a problem. So just cross out example 2, and we'll go to example 3. Okay. All right. So here we go. Come on back. Go to example 3. Go to example 3. We'll go through the 5-step process again, and I'll walk you through this one, and then we will go through some of the FRQs that I gave you yesterday. So first thing, what do you notice? The question would be, can we separate the variables? You want to be, somebody mentioned squaring both sides. You need to be careful because you don't really want to deal with derivatives squared because it ends up with a little bit of a sticky situation and it's not a second derivative. So the first thing you're going to do is this. One operation on x and y can be split into 2 operations. Then what are we going to do? Cross products. And I'm going to write it as y to the 1/2 dy equals x to the 1/2 dx. Why would I put them as x to the 1/2 and y to the 1/2? So I can use power rule on them. They're easier to differentiate that way. Good call. Once we're there, we'll integrate. Integral of y to the 1/2, y to the 3/2 times 2/3 equals x to the 3/2 times 2/3 plus c. You need a constant of integration on one side or the other. You don't need it on both, just to reiterate. Okay. You could solve for y at this point, but I'll pause here and talk about what would it look like to solve for y. You're going to multiply both sides by 3/2, and you're going to 2/3 power everything, which is really weird with a c in it. That's why my suggestion of solving for your initial condition now, I think, is pretty solid. So use your initial condition, 0, 9. Your initial condition, we've got 2 times 9 to the 3/2 all over 3 plus, or I'm sorry, that's an equals. I did that in the last problem too. That's an equals 2 times 0 to the 3/2 divided by 3 plus c. This part's just 0, right? 9 to the 3/2, that's a square root of 9 to the 3rd power, that's 27. 27 over 3 is 9. 9 times 2 is 18. So we should get the c value of 18. Okay. Just to be clear, if you were to plug in your initial condition at another point, you may end up with a different C value, but again, focus on the final result for the particular solution. Once we get C equals 18, we'll go ahead and say 2y to the 3 halves over 3 equals 2x to the 3 halves over 3 plus 18. Now what? Solve for y. What should we do first? Times, let's multiply by 3 halves. We can do that in one step. So let's multiply by 3 halves. So this becomes y to the 3 halves equals x to the 3 halves plus 18 times 2/3. Let's divide first. 18 times 2/3 is 12. Is that right? 18 divided by 3 is 6. 6 times 2 is 12, right? Good so far? Okay. Solve for y. What do I have to do? Excellent. Raise both sides to the 2/3 power. Do I need to worry about the plus or minus scenario here? No, because I'm not square rooting. Okay? Cube rooting. So here's your particular solution. Okay? Questions so far? Example 4. I want you to take a few seconds, and I've got a slice of pie for the first person who can successfully separate the variables. Go. It was some of you used a loose definition of separating the variables. I get that. You can try all you want algebraically here. The point is, and I'll do one example. One method you could do is you can multiply both sides by dx and get dy equals x dx plus y dx. The problem is, when you get to this, is this term right there. In order to integrate, you can't integrate y dx. It's not going to happen. So these variables on this problem cannot be separated. Now, that's the bad news, that this is not a separable differential equation. The good news is, on your AP exam, they want you to solve a separable differential equation. If they ask you to solve a separable differential equation, what are they going to give you? A separable differential equation. Okay? So they're not going to give you one of these, but I wanted to put it in here just to get a feel for it. If we don't have a separable differential equation, there's not an algebraic method to use to solve this, but what could we use? You could make a slope field. Okay? And that's why slope fields are that, we talked about it the other day, slope fields are a good universal tool because they work for every differential equation. This algebraic tool that I'm showing you today only works for separable ones. Let's do this. Will you take out your FRQ packets? We're going to start with 2005 question 6. All right. That's me. That wasn't me. All right. We're going to focus on, we'll talk more in a minute. We're going to focus on 2005 question 6, and we're going to do part C together, and then I'm going to give you one more to try with a friend. So, it's the third one in. So, front of the second page, supposedly. Okay? So, first of all, can we separate the variables? The answer on all the FRQs is going to be yes. You can separate the variables because they're not going to give you one you can't. So, cross products is a good way to go here. Let's do the y's on the left, though. This is y dy equals negative 2x dx. That's your first step, is to separate. Now, Did I mention you don't get any points if you don't separate the variables? If you don't separate the variables, you will get 0 out of 5 on this. This is worth 5 points. You promise you will get 0 if you don't separate the variables. You then need to integrate both sides. That's the second point. Integral of y, dy. Y squared over 2. Integral of negative 2x. Negative 2x squared over 2, right? So negative 1x squared plus c. If you forget the constant of integration, you're probably not gonna get any points beyond that. Question? No question? Uh-oh. Yes, you're gonna lose points. Uh-oh, you're gonna lose points if you don't put the constant of integration on. Okay? You don't seem too upset about losing points. Okay? This is part C. Yep. Yep. Okay? Next step, before you solve for y, I like this step. You could solve for y now if you wanted to, but I think it's a good idea. Algebraically later on, you can try it both ways to convince yourself, but I try to do the initial condition at this point. Negative 1 squared over 2 equals negative 1 squared plus c. We've got a couple of different squares here, and you have to treat them differently, right? Left-hand side, what's this value? Positive 1/2. Right-hand side, what's this value? Negative 1 plus c, right? Nice example of two negatives being squared and the order of operations making a difference. So 3/2 is your c value, or 1.5, however you want to do it. Okay? Then I go back up here. And I take my equation that I integrated, and I add the c value that I'm told. And now I solve it for y. I'm going to clear the fractions by multiplying by 2. If we're particular about our mathematical definitions now, this is the next statement. I think you can logically skip the absolute value and go right to the plus or minus. Do I have a particular solution? I do not have a particular solution. I have two particular solutions. Okay? Now, based on visual inspection with your initial condition, which one do I want? The plus in front of the root or the minus in front of the root? You need one of the two. Which one? What's the y value on your initial condition? Negative 1. How do I get a negative y value out of this? Because y is less than 0 in the initial condition, you have to use this one. Negative square root. Negative 2x squared plus 3. That's the one that you want. Does that make sense? You could plug it in and check if you wanted to, but because it's just a plus or minus and you know that your y value is negative in the initial condition, the only way to square root something and get a negative is if you multiply it by a negative after you square root it. Cool? All right. I'm going to stop the recording at this point, and then we're going to work through the very first problem, 2000, the one on the front of the packet. We're going to go through together before I let you go for the weekend. 2004, question 6. There's some book work in there for homework. Give it a shot.